Hi, this is Wang Chen, and this is my short screencast for DSA5205 Project 1. I'll walk through tasks 1 to 3, show my code running in a clean environment, and explain the key results and what I learned. So I'll start with task 1. Here is the code, and in task 1, we reproduce the ridge benchmark from the virtue of complexity in return prediction. And the data is simulated in here, the task1 py. Each observation has random features S and the target R. The true complexity C equals 10, and the observed CQ varies from 0.5 to 10. And this section evaluates the ridge estimator across different penalties Z. And here we run the script, and we can see that in the figures here we produce 4 pictures, and in output we have this DGP run.mpz and task1 curves.csv. Yep. And let's look at the pictures. So we can see the typical peak near CQ is approximately equal to 1, and moderate shrinkage archives the best R square and sharp ratio, which confirms the ridge-based theory. In this task, I learned how ridge keeps coefficients bounded even between when P is greater than T. And let's look at task 2. And here we have task 2. In task 2, I reuses the data generation process saved in DGP run, which is produced from task 1. And I changed only the regularization from L2 to L1 by using lasso. The goal is to see how sparsity affects the same matrix. Now let's run the script. Okay, now let's go to figures, and we see here is a new picture for the task 2. And this figure shows for 4 panels, R square, expected timing return, sharp ratio, and coefficient norm. When alpha is large, most coefficients become 0. Performance flattens. And around alpha equals to 0.01 to 0.05, the matrix improve but never beat ridge because the true beta star is not sparse. So this illustrates the bias variance. Yeah, bias variance trade-off between ridge and lasso. And for task 3, let's run task 3. And I choose different models for each set based on validation results. For pair A, like it looks nonlinear, so I used random forest. And pair B and C were smoother, so I used ridge regression. And here is the random forest, and BC is the ridge. And I think these choices align with the theory. And okay, so throughout the project, I learned 3 key lessons. The first one is that ridge regularization stabilizes predictions under model misspecification. And the second one is that lasso enforces sparsity but can underfit dense signals. And the third one is ensuring reproducibility is as important as the model itself. And that's it.